Hi guys. Well, congrats on getting through the second exam. Now we begin on chapter 7, which is probability and statistics. And we're going to start by talking about how to visualize data and probability. And that tool is the bar chart, is our first tool really. So bar charts. This gives us a way of visualizing relative quantities of things. So let's do an example. Suppose you give a yes/no questionnaire to 20 people. Okay. And get, let's say, yeses, you get 12, and no, you get 8. Well, if we want to put this into a bar chart, what that would look like, say this is 4, 8, 12. Then we have our yes category and our no category. Alright, so yeses were 12, so let's go all the way up to 12. And the no's were 8. I'm going to fill that in. Alright, it's pretty straightforward. We have some finite number of sort of bins. In this case, we had 2 bins, yes and no. And then we put a bar with the number of things in each bin. Now, what we often do is instead of, so this would be absolute quantity, I guess we could call it. So absolute quantity. What we often are interested in what we call relative frequencies. So it's a little bit like probability. So the frequency of the yeses is simply the number of yeses divided by the total number of responses. So this is 12 over 20 equals 0.6, and 8 over 20 equals 0.4. So these are frequencies. I'm saying 60% of the responses were yeses and 40% were no's. And we can put those in a bar chart as well. So we'd have yes and no. Then instead of 4, 8, 12, what we'd have is 0.2, 0.4, and 0.6. Oops. And we do exactly the same thing. Now it should be noted that the shape of the bar chart is the same regardless of whether we're doing absolute quantities or in this case relative frequencies. The shape is the same. All that's different, shape is the same. All that's different is how the y-axis is scaled. So really, to make it frequencies, we just scale the y-axis by the total amount, and then we get our frequency bar chart. And it's basically the same idea as if we were asking about what the probability of getting a yes or no answer is, except we haven't specified any sort of experiment here. We're just sort of talking about the data that we have. So if you were to select a random response from the questionnaire, it would have a 60% probability of being yes and a 40% probability of being no. If you were to select them with even probability of any given answer being chosen, etc. But since we haven't really specified any experiment with outcomes, we're just talking about the data. We don't necessarily call it probability. So let's do an example. So this is the first example on the worksheet. So you have marbles in a bucket, and so the 25 of them are red, 45 are green, and 30 are mauve. Just to be a little more interesting, I guess. So then the frequency, is just the number divided by the total. So the total here, let's see, 25 plus 45 is 70, plus 30 is 100. Okay, so then the frequency is 0.25 for red, 0.45 for green, and 0.3 for mauve. And so we simply plot that on our bar chart. So red is 0.25, well, 0.2 is here, 0.3 is going to be halfway in between, and then 0.25 is going to be halfway in between that. So it look like that. Obviously it doesn't have to be perfectly accurate. Green is 0.45. That's going to be, again, halfway between 4 and 6. So like that, and then mauve is at 30. So, oops, it look like that. Okay, so that's our frequency bar chart. And if you were to specify the experiment of selecting a marble at random, this would be the plot of the probabilities of it being red, green, or mauve. We haven't specified that we're doing anything with an outcome. This is just a sort of amalgamation of the data. So we call it frequencies instead of probability. All right. So that's all well and good, but if we have, so one thing to note here, so note our data in this case, so this is not something you have to include on your answer, but I'm just using this to illustrate the next point. So our data here are these categories. So it's either red, it's green, or it's mauve. So our data is not numeric. So data is not numeric. It's a color, it's not a number. And now we have numbers of the different colors, but our categories themselves, so maybe instead of data is not numeric, we'd say, so the categories aren't numbers. Are not numbers. And that's important. And that's important because if they are numbers, if our categories were themselves numbers, then our frequency bar chart is a histogram. So let's look at the next example. So a recipe pamphlet contains 50 simple recipes. The number of ingredients required by the recipe is given in the table. So what this is saying is that two recipes have only 3 ingredients, 3 recipes have 4 ingredients, 15 recipes have 5 ingredients, 20 have 6 ingredients, and 10 have 7 ingredients. So now if we make a bar chart of this data, either in absolute quantities or frequencies, we call it a histogram. Right. The only reason it's called a histogram now is because it's because the bins themselves, the categories themselves, are numbers. These are numbers. I'll let you guys do this one on your own, but like I said, it doesn't specify if it's supposed to be a frequency histogram or just quantities. So you could do it however you want. You could do it in frequencies or not. But yeah, so I'll have to make that bar chart. All right. So let's talk about the next example I want to talk about. So this isn't on the worksheet, but I just wanted to talk about the example of a probability histogram. So probability So what this is that if we have an experiment and we have numeric outcomes, then we can make a bar chart for the probability of each outcome. Bar chart for probabilities of each outcome. So one experiment that might have a numeric outcome is that, so experiment. We roll a die 2 times and take their sum. So, or rather, roll a pair of die. Roll a pair of dice, and record the sum. And, well, this is, if I don't specify, it's assumed they're 6-sided die, and this is something we've done a few times. So I'll just give the probabilities here. So, right, the probability of rolling a 1, the probability of rolling 2 ones, right, so you're getting a sum of 2, is 1 out of 36. And this is equal to the probability of getting 2 6s. So it's the probability of rolling a 12, or getting a 12 in this roll. And similarly, we have the probability of getting 11 equals the probability of getting 3 equals 2 out of 36. The probability of getting 10 equals the probability of getting 4 equals 3 out of 36. Obviously, some of these fractions we could simplify, but I'm leaving it like this just so they all have the same denominator, and it's much easier to see what their relative values are. Probability of 9, getting a sum of 9, is the same as the probability of getting 5. That equals 4 out of 36. And the probability of getting an 8 equals the probability of getting a 6. That equals 5 out of 36. And then we're left with the one in the middle, which is the probability of getting 7, which is 6 out of 36. All right, so we can plot this, and we get this picture. So this is the probability histogram for rolling a pair of dice and recording the sum. Alright, so this is what it looks like. Now, the reason we wouldn't call something a histogram if it wasn't numeric data is because when we have numeric data, there's sort of this necessary order to the bins, right? We have them in their numerical order, smallest to greatest, and that gives the histogram a shape. So, whereas before when we just had colors, right? If we scroll back up, there's no reason I listed them red, green, mauve. I could have listed them mauve, red, green, or whatever. And so the actual overall shape of this thing is irrelevant. Whereas when we have numeric data, the overall shape, in this case it's like I have a peak there, is actually meaningful. And this, well, particularly this is saying that 7 is the most likely. So 7 is special in a number of ways in this example, and I'm going to use it to segue into the next topic, which is talking about the median. So let's think about the ways 7 is special. So 7 is special. Well, for one, it's clearly the highest value. So in this case, it's the most likely outcome, right? It's the most probable outcome of any individual outcome. So it is most likely of any single outcome. That's true. And the way in which it's special that we're going to care about right now is actually a little bit subtler than that. So this is just sort of as an aside, right? This being the most likely of any single outcome is what we would call the mode. We're not really going to talk about that, but since I mentioned this, I thought I would give you the proper name for it. It's the mode of the histogram, whatever. The way that 7 is special in this case is that it's in the middle in a very sort of specific way. So it's in the middle in what way is that? Well, so you're just as likely to get a sum that's bigger than 7 over here as you are to get a sum that's less than 7, which would be over here. So either side of this 7 are equally likely as events. So the event that you land here, right, which is to the less than 7, is equally likely as this event here, where you land more than 7. So this particular way in which 7 is special, it's in the middle in the sense that probability of the outcome being less than 7 equals the probability of the outcome being greater than 7. So in terms of the probabilities, it's in the middle. It turns out it's also in the middle, right, just in terms of number. Between the numbers of 2 to 12, 7 is smack dab in the middle. But that's actually not actually relevant to this probability being in the middle in the probabilistic sense. And what we call this is that it is the median value. So 7. So this property of having greater than and less than being equally likely is what defines the median. So 7 is the median. All right. So now we're going to talk about how to calculate the median. But we're just going to do sets of numbers. Given a finite set of numbers, how do we calculate the median of the set? And then we're going to bring it back into probabilities later on. But so calculate median. Calculate median. And it's possible some of you remember how to do this. I don't know if they taught it to you in high school or whenever. But just in case you don't remember, right? There's basically 2 steps. Step 1 is sort your set of numbers. So sort them. I guess from least to greatest, but it doesn't really matter. You could sort it from greatest to least. I can't write today. E-A-T-S-T. Okay. So sort them. And step 2. Well, it depends on if you have an odd number of numbers or an even number of numbers. So if you have an odd, odd number of numbers, that's the simplest case. You just take the middle value. Just take the middle value. And I mean middle by place. So the middle value, so alright, a little aside here, so example. If we have the set 1, 2, 7, right? These are already sorted, so step 1 is completed. The middle one, there's 3, so the middle one is the second one, so the median here is 2. All right. Then if there's an even number of numbers, well, if there's an even number, then we kind of have 2 middle numbers, and well, if that's the case, we have to take their average. So just take average of middle 2. So this sort of illustrates how the median is sometimes not even in the data set at all. Right, so an example of this one would be if we have the data set 1, 3, there's 2 middle values, which is both of them. So we take their average, which is 2, so median equals 2. Right. So now the next part of the exercise is just computing the median value for a couple sets of numbers, and this should be pretty routine. I can show you for the first couple, and then I'll let you do the last ones by yourself. So let's see, for the first one, right, we have 5 numbers, so that's an odd number, and they're already sorted for us, so that's fine. So we just take the middle value, which is 3. And right, so for the next one, so right, median is 3. For the next one, we have an even number. We have 4 numbers, so we look at the middle 2 and take their average. So 3 plus 5 over 2 equals 4. So that equals median. All right. So the last example I'm going to do for you is this one, and I just want to show how as soon as you have repeating numbers, you don't do anything different if you have a number repeated. So if we have 1, 1, 2 as our collection of numbers, they're sorted, they're in numerical order, so again we just take the middle place, which is the second place, which is here. So in this case the median is 1. Now, one thing to notice here is that the median doesn't change if we just change the value of the endpoint. So if we look at instead 1, 1, 100, this has the same median. The median is still 1, which is the middle value. If we have 1, 1, 1000, the median is still 1. Right? So the value of this endpoint number doesn't actually affect the median whatsoever, which in some sense is both good and bad depending on what you're trying to capture, right? But it's just the way the median works. It's not sensitive to far outliers. All right, and we'll talk more about this in the coming lectures, but it's something to keep in mind. All right, so for the next 2 examples, I want you to do them on your own, and well, that's that. That's the median and bar charts. All right, bye.